Today I'm going to talk to you a little bit about understanding the relationship between income, education, and partisanship, which is one of the substantive applications of one of the methodological pieces of research that I do. So in your homework set, you were looking at what is the chance that somebody votes a Republican or Democrat based on what their income and their education is. I'm going to use a little bit of a tweak on that data set. Mostly because we can't ever actually know what the chance of somebody voting for any individual voting for a Republican is. Like, I can't say for myself, actually maybe I can say for myself what is my chances of voting for somebody, but I probably couldn't point to any of you guys and say you have a 92.2% chance of voting for this particular candidate. But I can tell you that any given congressional district in the country that 62% of them voted for Hillary Clinton. It's hard to show you data that is binary, that is only a yes or no option. It's fairly easy to show you guys something where I can actually measure this was the percentage of the county, of the district, that did a particular thing. So instead of looking at individual data, I'm going to be looking at aggregated district level data. I'm going to be looking at every district in the United States represented by a Democrat, and looking at what's the relationship between the percent of the Democratic vote in that district in 2012 and the affluence of that district, how much of that district earned over $25,000, and what percent of that district had a college degree. The full equation for this, the way that statisticians write it, is that we say that Democratic vote is predicted by beta 0, it's a constant, plus beta affluence, which is your slope, times the percent of the district that's affluent, plus beta college, which is the slope for the percent of the district that had a college degree, plus epsilon. Epsilon is our error term. We're going to see very shortly that those error terms are really important in social science data because our data has a lot of errors. That's every point there, that's one individual district. It's pretty well spread out, it's fuzzy. You can still make inferences though. So I'm going to be using different numbers from the ones that you guys have because they're going to be the ones for the real world. And I'm going to be able to say that in 2012, for Democratic districts, the relationship between a Democratic vote and Democratic districts are districts represented by a Democrat. And I'm just choosing Democrats just for data cleanliness. There's a couple of oddities that showed up with Republicans as well, so I just pulled them out. And I'm going to show that the relationship between the Democratic vote is defined, and affluence in college is defined by this equation. Namely, 70.96% minus 0.566% times the percent affluent, plus 0.488% times the college, plus some error term. So in statistics, we're all about interpretation. And so what this means is that holding college constant, 1% increase in a district's affluence is associated with a 0.566% reduction in the vote for the Democratic candidate for president. What's the association between college degrees and Democratic voting? What's the number? Yep. Is anybody surprised by this? It turns out that it's actually a little bit of a modern phenomenon, certainly at the individual level. So this is, your data set holds, the data that you had in your homework holds for the modern era for the past like 5 or 6 years. If you look back further in time, it actually gets a little bit fuzzier for the individuals. But interestingly, when you aggregate to the district level, this actually still holds for most of recent history. There's a difference between aggregating data and looking at individual level data. So even though it's true that richer people vote more Republican, is it true that red states are richer? No. Why?
Because they're normally more rural.
They're more rural, yeah. So you've got a concentration of wealth in a particular bunch of areas that that are the very urban, dense areas. But even despite the fact that there are some urban, dense areas that are very democratic and rich, that doesn't mean that being more rich individually makes you more likely to vote Republican. It's kind of a funny aggregation issue. I'm going to add in a little bit of statistical jargon onto this. So 0.566 and 0.488, those are both the beta terms. Those are both our slopes. In multivariate analysis, what's another thing that you could call those slopes?
Directional derivative.
It is a directional derivative. It's a very special case of directional derivative. It's a partial derivative, which is the directional derivative when the other thing is held constant, or everything else is held constant. So I've got a really nifty graphic here. This is the regression plane based on these three variables. So this is the best fit plane for predicting percent voting for Democrat based on the percent in college, how to have college degrees, and the district affluence. This means is that if I was going to choose any specific point, I could say that if I have 45% of the district that's affluent and 30% of the district that has a college degree, then I could predict a particular point for what percent of that district should vote Democrat. But it's going to be fuzzy, because if you actually look at the data, it's fuzzy. We're looking at best relationships. Over on the right is projection. So here I'm looking at the full plane. This is just looking at what happens if I just look at the slice on that green line. It's a negative slope. What is the slope of that line? There's the other one, it was the 0.566. I've got confidence errors around here, and this is one of the cool things we get to do in statistics. We get to say, how confident are we in this slope? And in this case, we are very confident that that is a negative slope. And I know that because no matter where I put a line in that purple area, purple shade, it's always negative. But if I'm going to also look at the relationship, not just for income and education, I can flip this plane and look at just affluence and college degrees and ignore the percent of the county that's voting for Democrats, right? And that's what this graph is. It's a pretty tight relationship between education and income, right? Anybody surprised? This is why you guys are all here, right? But it's not just that going to college is going to get you more money. There's actually a reverse causality there too. What's the reverse causality?
More money have more likely to go to college.
More money, you're more likely to go to college, right? And more likely to go to a higher college, which makes you more likely to earn more money, which makes you more likely to have children who benefit, and the cycle goes on. So we can plot a line that is showing the relationship between affluence and college. Does anybody see where I'm going for directional derivatives here? Not yet? That direction. And that is going to be precisely this red line on the graph. So when we were looking at the 0.566 and the 0.488 coefficients, those were depicted by these two green lines, right? So look at the directional derivative, we look along the red line. That relationship is defined by this equation. This is the percent college is equal to negative 0.392 plus 0.96 times the percent of the district that's affluent. So basically, does anybody want to interpret that in English terms? What does increasing 1% of affluence cause for college?
0.96.
0.96 what?
Percent.
Mm-hmm. on average, when you increase your affluence, a district affluence by 1%, you get a 1% increase in the percent of the district that's going to college. So the question that I have, and one of the reasons, the big reason why I did this, in addition to the fact that this kind of data causes all sorts of weird interpretation issues in statistics, is it actually meaningful to hold education constant or to hold affluence constant when you have a fairly strong relationship between these two things? So when you hold one of these things constant, you can think about the partial derivative as just being a line fixed at a point going straight up through the plane, right? There's a problem here. My data ranges from about 10% with college degrees all the way up to 70% with college degrees. If I'm looking at this cross-section, can I cover that range of data? I really can't. You can get some of them. So if I'm looking at a narrow cross range, I can probably get 30 districts in here. But it's not going to cover nearly the full range of the entire area. But that doesn't mean it's not meaningful. In this case, I can predict that if you go from the bottom of this arrow, held at this point, to the top of this arrow, you're going to increase the percent of the district that's voting for the Democrat by 13.8%. It's a lot. And that's going up. What happens as you go in this direction along the plane? What happens to the percent that's voting for Democrats? It's down. And so what happens what's going to happen as you go in this direction? Somewhere in the middle. I think that you guys had it come out to exactly 0, or yeah. I'm going to have it come out to not quite 0 because I'm dealing with real world data. So it's a statistically significant and substantively meaningful change in Democratic voting when we're looking just straight up. But looking at that in that direction is also a direction that we could really want to look at. I'm going to make a very quick note on statistical significance. I hate the word statistical significance because statistical significance in English, it means important. Significant in statistics only means non-randomly different from 0.
Oh yeah, I was just gonna ask, like, along that line, like, would are you, like, trying to, like, add an interaction term here that would, is it significant statistically, is what I have to ask?
This is different than interaction term. This is literally a directional derivative, and remarkably, it's a funny thing. If you talk to statisticians, almost all of them will say, what do you mean a directional derivative? And it's largely because we don't think about these things in 3 dimensions or more. I've been struggling for quite some time on why we haven't done this yet. But yeah, it's not actually an interaction term. An interaction term would say that the slope changes as you move along. And what I'm just saying is that if you change your direction, you get a different interpretation and a different slope. For those of you who have done this kind of thing, this red line is also a principal component, and it's a completely radically different interpretation of a principal component than I would expect any of you to have seen. So this slide got a little bit wonky, but as we're looking along this red line, going all the way from the bottom to all the way at the top of that arrow, you see a negative 4.916% change in the percent of the district that votes for Democrats. So when we're looking straight up and down, we had a 13% change over this relatively narrow range of data. This entire range of data is only negative 0.4619% change. Meaningful, but as it turns out, not statistically significant, which means that in statistics we say that we don't know what to do with it. We don't know if it's random. It very well might randomly just be a kind of artificial noise thing that we can't conclude is truly negative. So what I'm saying is that not only do we want to look at our partial derivatives, because partial derivatives are handy, we also want to look at the directional derivative and interpret it in this very specific way, which is fairly simple. Saying that a 1% increase in district affluence is associated with a 0.96% increase in college degrees and a 0.070 decrease percent increase in voting for the Democratic presidential candidate in 2012. And again, that change in voting is very small, very well may be due to chance, it's not statistically significant. Put this in a few, I'm not quite sure if my notation is your notation. And I'm sure that I have a lot more words than you guys have in math. That's because in statistics we deal with actual concepts and we don't want to just label everything I or X. So this joint direction is a directional derivative. It's an additive sum of my two slopes, the slope on education and slope on affluence. And I have a question for you guys. So the first equation is just saying, hey, the slope for affluence, beta affluence, plus 0.96 times the slope for college, beta college, is equal to the slope for the joint direction. Then I put that in some direction in partial derivative terms. And then I pulled out this 0.72. Why did I pull out the 0.72? It has to do with that problem.
You get a unit vector.
Unit vector.
Hey.
Why did I not want to make the unit vector at the top? What's the interpretive utility of not having a unit vector at the top?
You can get a line equation.
They're all lines.
Your slope is like over 1, so it's like a 1%.
You can say a 1% increase in beta affluence causes a 0.96% increase in college. So this is where stats differs from math. I really want to interpret this stuff. And I want to be able to put this in as simple terms as possible. So even though unit vectors are absolutely brilliant for everything math, it makes everything super simple. When it comes to interpretation, sometimes it's useful to denormalize your coefficients. Don't do that for math though. It'll make your life very, very hard. And I know this because I've had to denormalize everything. Yeah, so joint directions are useful. Sometimes it turns out oddly that, and the real reason I started this was that sometimes you can't actually tell a difference in either the green directions, and sometimes you can only tell a difference in the joint direction. And that is one of the values for being able to think of these as directional derivatives.
All right, lovely. Some more questions? I have a leading question that I already know the answer to, I think. Who thought of using directional derivatives in statistics, and when was that invented?
It was invented about 2 years ago by me, and so if you to go talk to your stats professors about directional derivatives and statistics, they are probably going to look at you kind of confused until I finish talking to all of them. Yeah, it's a thing. Turns out that it's not only that you can interpret things, it turns out that if you start thinking about things as directional derivatives, just about every every regression model variation that you can think of can be thought of as a directional derivative of a full model, and often you can get much better precision if you think of it as a directional derivative, and I get to write the paper saying that.
What software do you use to make the multivariable regression model?
So the multivariate model is using R, and although the really cool part of this is this 3D graphic, and that one you can make in Python, Java, or R. Can't make it in Stata, sorry. But you can make it in any of those three languages. The more that we see the data in 3 dimensions and we can actually manipulate that, I think the more that we're going to get some really foundational insights that we haven't had before about regressions.